Now we're into the next little segment video here of acids and history. And we looked at in the previous video the work of Antonio Lavoisier, who said that certain non-metal oxides, when dissolved in water, produce acidic solutions. And so therefore, since non-metal oxides have oxygen in them, such as carbon dioxide, nitrogen dioxide, sulfur trioxide, that that oxygen had some acidic properties. And so he believed that acids were those that had oxygen in it. But of course, we had limitations to his theory, and the limitations were that there were substances that had oxygen in it. For example, the metal oxides, sodium oxide, magnesium oxide, they didn't produce acidic solutions. In fact, they produced basic solutions. So his oxygen theory of acids just didn't really hold up. We also found that there were substances that had no oxygen in it, also had the ability to be acidic, such as HCl. And then we moved on to Davy's theory, which Davy said that Humphrey Davy, and we highlighted the H and said that Humphrey Davy had hydrogen. And so he said, okay, acids are those that have a replaceable hydrogen. And then we had some problems with his theory as well, and that there were compounds out there that had hydrogen present in them but were not acidic, such as ammonia. We had ethanol that had hydrogen in it, not acidic. So now we're on to the next person here, which is Arrhenius. Right, Svante Arrhenius, and then the next video we're going to be looking at the Bronsted-Lowry theory. So let's get into Arrhenius' theory. So Svante Arrhenius investigated electrolytes. And remember, electrolyte is a solution that has ions, free mobile ions that can conduct electricity. And basically the really core idea here is that Arrhenius' theory is involving water and the release of H+ ions or OH- ions for bases. Right, and so his fundamental theory was that acidic solutions are electrolytes. They can conduct electricity. The reason why they conduct electricity is because they release a H+ ion in water. And I've put in water there in blue because that's a fundamental important concept about the Arrhenius theory. So when we're talking about that, we need to make sure you're writing your equations with aqueous, right, symbols here. So if we're let's say we're doing HCl, then we have to have aqueous HCl, not gaseous hydrogen chloride. Okay, so make sure you've got to put the aqueous there because that's enforcing Arrhenius' theory that you need water. Now, this is the same for bases. Bases can be electrolytes as well, but they release OH- ions into the water. But the thing about this here is that this theory could explain what the differences between strong and weak acids based on the amount of dissociation they have. Strong acids were those that broke up into ions more readily, had greater dissociation, whereas weaker acids did not break up or dissociate into ions. And we can see this here. I've got a picture up here that I did in the lab, and from this picture, it's a composite picture, me and my photography. So I took multiple pictures together to show you that we have 1 molar HCl. Okay, I'll just de-draw on that picture. And here we go, switch to the laser. So we have 1 molar HCl, you can see that is bright. Then we have 1 molar sulfuric acid, not as bright, interesting, we'll talk about that later. But then we have 1 molar acetic acid, which is very, very dim. And then of course we have no conductivity for glucose solution, and then no conductivity for distilled water. So here's the video of all that happening as well. And a lot of people are surprised when they find out about water because it's the ions in the water that cause conductivity. Water itself, even though it's a polar molecule, does not conduct electricity very well. Okay, but when you hop into water, a lot of salts from your skin dissolve into the water and therefore make the water more conductive. So the Arrhenius' theory can explain that we have water involved and the release of ions, and that's the one that pretty much we do in the junior school, right? But we've got to get more sophisticated than that because there's examples now, of course, where a material can be acidic or basic but not release H+ ions or OH- ions. Ammonia is the typical example. Ammonia is a base, but there is no OH- ions that ammonia releases into solution. So what's going on there? Well, I'm glad you asked, because in the next video, we're going to explain that concept with the Lowry-Bronsted definition. See you then. Right, before we go to the next video, I want you to check out more courses that we have here on our YouTube channel, which are just small snippets from the actual bigger courses that we have on theflipteacher.com. Of course, with all of our courses, we try to incorporate practical sessions. We have study cards, we have posters that you can print off and stick around your room and do a lot more. We have up to 68 or more videos per course. That's like 9 to 10 hours of material that really delve deep into the syllabus and looking at essential content, skills, mathematical manipulations, and a lot more. So if you like that, go over to theflipteacher.com and check it all out, and I'll see you in the videos.